Alright, time for another math easy solution. Today we're going to discuss, well, another problems plus example. This is the fourth one of this series. Basically, look at an example that involves mathematical induction. Before I get to the example, I just want to go over briefly the principle of mathematical induction. And this one basically states, let's say, let Sn be a statement about a positive integer here of whatever n is, whatever, like either 0, 1, 2, 3, etc. Now suppose S1 is true. So if S1 is true, and then also if you suppose that Sk plus 1, or the one after the first one, is true, whenever Sk is true, then basically S of n, or of the positive integer, is true for all positive integers. So what this means is if you have an S1 value, so then if this first one is true, then all it means now, because if you suppose that this statement is correct, number 2, then S2, which is k plus 1, if k is 1, this is k equals to 1, this is k plus 1, then this is true, and then you could apply this as well. Now if you have a new one, k equals to 2, S3 is equal to, well, k plus 1, so that's 3 here. So then if this is true, then you can keep doing this forever and ever. So then you're going to go S4, etc. And then, so this is just a way of mathematically inducing or deducing that S of n is true for all positive integers. Now we'll go through an example on this to just illustrate this further. So now to illustrate this mathematical induction, I'm going to go over this problems plus example, which is in my calculus book, which has these hard examples at the end of each chapter. So now we'll go over this one here. It's really useful to understand mathematical induction. Basically it states if f of 0 of x is equal to x divided by x plus 1, and f of n plus 1, or the next one after, of x is equal to f of 0, and this one is circle f of n. If you see my other video on combining functions, this just means, this just means f of 0 of f of n. So this is inside it. You just put a circle here. You can see a video link below, one more on this. So basically for n is equal to 0, 1, 2, or 3, 4, basically positive integers here. So now that the question states find a formula for f of n of you have fn of x here, or just a general one for any positive integer. So now to do this, we first have to actually, instead of just thinking of it generally the way, now let's just find something that's simpler. We'll look at n is equal to 1, 2, and 3. So yeah, we'll use the first three integers, n, 1, 2, and 3, or basically solve for f1 of x, f2 of x, and f3 of x first, and hopefully we could see a pattern, and we could basically guess what our general formula is, and I'll show you how to prove it with mathematical induction. So let's go with f of 1 here. So then we look at this general formula here. So f of 1 here, this equals to f of 0, so it equals to f of 0, and then this is going to be n, and n in this case is going to be 0 here, because this is the next one. So this one, all it's saying is we look at the one previous. So f of circle, it's not multiplication, it's a circle, or of, so this is going to be a 0, and this equals to f of 0 of f of 0. So we plug in this function inside it, and we know that this one is equal to, well, now we're going to plug in x over x plus 1, because that's what we're given. So now we plug in x divided by x plus 1 inside each x. So this is just going to equal to x plus 1. So we put the x divided by x plus 1 inside this x, and inside this x as well. So we're going to have that divided by x plus 1 here. Now we could simplify this further by multiplying by common denominator on this 1's here, so we could add these together. So we'll just go x plus 1 divided by x plus 1, add these up. This is just going to equal to now x plus 1, and now as you can see, the bottom denominators are the same, x plus 1, and then the only thing that adds is this x and x. So we're going to get 2x plus 1 here. And now this divided by x plus 1, and this cancels out, so we're just going to be left with this formula, x divided by 2x plus 1 here. So we get this one here for f1 of x. So now if we do similar thing for f2 of x, now this is just going to equal to f of 0 of now f1 of x, and we know that. Yeah, so we know what f1 is, and that's this one right here. So we just plug in now. So yeah, we just plug in this x divided by 2x plus 1 inside the f of 0 function. So yeah, we plug it in this one here, and then if we again times the top and bottom by the common denominator is 2x plus 1. So now this would be exact same as the above, but now these add up. There's going to be a 2x plus x. So we're going to be left with, so we're going to be left with the exact same as before, but there's a 3x, and then there's 2x plus 1's cancel again. So we're going to be left with, let's write it down here. So yeah, so we get x divided by 3x plus 1. If we do the same thing for f of 3, we're going to get x is equal to 4x plus 1. Because we're just going to plug this back in to the f of 0 function, and then there's a 3x when we do the common denominator thing I did above, and we're going to have a 4. So as you can see here, we can guess that our f of n function, this one is equal to x. Now this one is always going to be greater than whatever this n is. So if this is 3, this is 4. If this is 2, this was 3. So we guess, and then this one, if this was 1, this was 2 right there. So then we guess that if this is f of n, then we're going to have an n plus 1. So whatever this is plus 1 times by x plus 1 here. And if it's f of 0, this is going to be a 0. It will just be x divided by x plus 1. So this is what we guess that our formula is. Yeah, so we basically guessed this is true from the pattern, and now to prove it, we have to look at this mathematical induction here. We could prove it by first proving S1 is true, and this one we have proved it. We have actually solved f1 of x, and that equals to this one here. So it is true for the first statement. So now we just got to find out if sk plus 1 is true whenever sk is true here. So we have to find out what this one is. Okay, so we assume that it's true for when n is equal to any random, let's say k integer. And so what this means is this f of k is equal to x divided by k plus 1 of x plus 1 here. So if we assume it's true, so if we assume this is true, we just have to find out what now fk plus 1. If this is true, when we assume this one is true, then basically by mathematical induction, then it's true. So we just plug this one in. This one's going to be f of 0, circle f of k, or this equals to f of 0 of f of k. Yeah, or this just means f of 0 with this inside it. And yeah, and when we plug this function inside f of 0, which was just x divided by x plus 1, we just plug it into whatever the x was. So we get something like this. And now we times this by top and bottom by common denominator, which is x plus 1, x plus 1 here, k plus 1. So the same thing here. This, and then we can add up this one here. And the only thing that we'll add right now is this x is going to go combine with this x plus 1 of x, or equaling to this one here, k plus 2x plus 1 on the bottom, divided by the common denominator, which is this. And as above, this one could cancel because you're dividing by the exact same thing, and this is going to be equal to x divided by x divided by k plus 2x plus 1 here. So as you can see now the number, this formula is equal to basically f of k plus 1. So as you can see, this is true as well. Yeah, this is true as well, because remember, if you consider this as n, so if this is equal to n k plus 1, then basically n plus 1 is just equal to k plus 2, because all you're doing is adding a 1 here. So as you can see, this one is true. Yeah, so basically now from mathematical induction, we know we've already proved that f1 of f1 of x is true, which is equals x divided by 2x plus 1. And now if this is true, yeah, so if we have this, if this is true, if fk is true, then basically fn, then this is basically the same for all of them. So we could basically imply fn is equal to, so fn of x, which is just x divided by n plus 1 of x plus 1, is true for all positive integers n. And it's basically for mathematical induction. Since this is true, f2 of is going to be true as well, and then basically you're going to have this repeating property here where fk plus 1 or the next one is true if this is true. So because this one has to be true if this is true, and then f2 is true, f3, etc. So it's a bit confusing, and maybe a bit confusing, but once you get it around your head, it's pretty obvious. Well, that's all for today. Hopefully you learned from this pretty intense example on mathematical induction. But basically, if you could try with a simpler function than these ones to see it. But that's all for today. Remember, you can download these notes in the Dropbox link below, and stay tuned for another easy solution.